Alexandra Weber from Telespazio, Germany, and I'm here together with my colleague Peter Franke, also from Telespazio, Germany, to present on AI-aware risk analysis and AI-powered security monitoring for space missions, which is partially based on joint work with Bettina Ballin from Fraunhofer SIT, Raphael Frick, also from Fraunhofer SIT, Cesar Guzman from Telespazio, Germany, Jeremy Meyer from RIA, and Jussi Roberts from ESA. I will start this presentation by giving an overview of our AI-aware security risk analysis, which was published at CYSAT this year. And then I will hand over to Peter to give you an introduction on our work on AI-powered security monitoring, which is work in progress. First, to give you a brief motivation, why are we looking into AI applications for space domain? As you might have noticed already, AI has become very ubiquitous by now. It's also evident from the program of this conference. Many talks are discussing AI. And also objectively, there have been many studies which show that AI is becoming very ubiquitous. For example, the McKinsey study, which showed that the use of AI in practice has doubled just in the 5 years from 2017 to 2022. And the space domain is no longer an exception to that. Examples of AI that is used in space missions include NASA, ESA, and also new space companies like Neurospace, which is applying AI for space traffic management. And these are just some examples. There are, of course, many more. But as you also might have guessed, the use of AI introduces some unique security threats, not just to space missions, but also to space missions. There are specific attacks like poisoning attacks or spoofing attacks, adversary examples that might be introduced and that we need to protect against. I have included here on the slide some examples of attacks on AI systems which go back as early as 2016 and have been ongoing since then and are still a very actively researched area, including different types of attacks, model extraction attacks, poisoning attacks. So this is definitely a very relevant threat. And in particular, it's a very relevant threat to space missions because of the high security criticality. So many areas of our daily lives rely on space services, and in particular also safety critical areas where security issues might very quickly lead to safety problems. This is also increasingly in the focus of attack research. This last year at SpaceX, there were multiple presentations, and also this year on the threats that AI poses to space security. Luckily, there are already existing knowledge bases on which we can build for this. Did I skip one slide? No. On which we can build for this. So in the space domain, the MITRE ATT&CK matrix is very popular for security risk analysis, and also the space-specific adaptations, the ESA Space Shield, and the Aerospace Sparta matrix. And there are also AI-specific guidelines to approach security risk analysis, for example, by the US Department of Energy, by OWASP, and by Microsoft Security. But unfortunately, these knowledge bases are so far rather disjoint. So the attack matrix and the ESA Space Shield, we did not find any explicit representation of AI-specific threats. And the Aerospace Sparta matrix, which was the most complete in this respect, also only mentioned isolated attacks and not a very broad overview, because obviously it's a very broad matrix covering a lot of different attacks. And the AI-specific guidelines so far have no mapping at all to space security assets, to space assets or space missions. And this is why our position is that we need actually a common knowledge base that maps the AI security threats to space domain use cases and space domain assets. And our goals with this paper were to provide a starting point for the discussion of AI security in the space domain, and also to provide an initial risk analysis on which we can build to refine and tailor it to further space mission and use cases. So we provide a preliminary analysis of the risk that AI introduces into the space domain with respect to 6 categories of use cases. Starting from AI-supported mission planning, AI-powered telemetry forecasting, AI that is used to support searching through heterogeneous databases of mission data, image classification for satellite images, assistance for operators that is powered by generative AI, and also the use of AI for processing huge databases of space mission logs. We provide a preliminary analysis of the risks that are introduced and also a collection of security controls that are tailored to addressing these risks that we identified. Before I give an example of the risks and controls that we identified, just a quick primer on which type of AI systems we are looking at, in particular machine learning systems. So in the space domain, we are looking at systems that are trained based on old mission data and then put into operational use to make predictions on live mission data, and which are developed based on the existing base models that are also, this arrow should actually be a diagonal in the slide, that are developed based on also the old mission data, which is needed to test that the system is working. And another diagonal arrow that should be there, showing that actually the live mission data might be used also in continuous training, so be fed back to the training to further improve the model after it is put into operational use. And we have identified in our analysis actually risks in each of these stages. And I will today show one example which affects the operational use stage, namely adversarial examples. Adversarial example attacks are attacks in which an attacker provides a sample to the system that is manipulated in a way that will change the prediction of the system in the attacker's favor. One specific type of these attacks are camouflage attacks, where the attacker manipulates pixels of an image in order to trick the classification system in a particular way. And how this could be relevant in the space domain is in particular showcased by this example, which is a picture from an attack that was mounted in 2020 on object detection systems. So in this case, the authors created an invisibility cloak that people could wear on their t-shirt and then be invisible to object detection systems meant to detect people. And on the right-hand side, this is a mock-up that I created, not completely seriously, but illustrating the principle that in the future satellite images could be manipulated by people putting such invisibility cloaks onto buildings, onto vehicles, in this case on top of our office in Darmstadt, to trick the satellite image classification into overlooking such buildings or vehicles maybe, and thereby manipulating information that is supplied, for example, to navigation systems or to intelligence services. Possible countermeasures that we considered that could help to protect against such attacks would be to apply adversarial training. So to include such adversarial examples already into the training data to make the AI system robust against such examples, and to leverage a particular advantage that we have in the space domain already, to apply contextual information to the processing. This is already in place for non-AI systems in the space domain, to validate the input data during the processing. For example, to prevent that bright pixels in the desert are misclassified as snow. And with this, I would like to hand over to Peter to show you that AI does not only introduce threats, but can also be leveraged actually to improve our protection.
Thank you, Alexandra. So yeah, I will go on and showcase a use case for AI in the space domain where we'll turn it a bit around and will not use AI for or not look at the security of AI, but the usage of AI for security. And the concrete use case is called the AI for security monitoring. And yeah, this is an ESA activity that is being run under the GSTP compendium. And the goal is to perform AI security monitoring for space missions, working on space mission data of actual satellites. And yeah, our company, Telespazio Germany, is leading this activity, and we are conducting it together, not only with ESA, but also with our partners, which are RIA and the Fraunhofer Institute SIT. And the general motivation, of course, is that space missions nowadays have quite a huge attack surface, and it's spread throughout the various segments. So we're considering the ground segment, link segment, and also the space segment here. And the general amount of attacks against all of these segments is increasing. And it is very important to attack, basically when we attack the system or when the system is attacked, that we detect it on time, because if it's not detected on time, the impact is much larger and might even lead to a loss of the mission. And to do this, there are a vast amount of data sources and also of data that should be considered. And doing this for a single human is quite challenging, which is why in this project we are resorting to using AI or machine learning techniques. And yeah, as said, there are a large amount of data and data sources to be considered. Let's look at what it actually is. So here we have a coarse overview of such a space system. As you can see on the top left, well, there's a flying spacecraft which is exchanging telemetry and telecommands with a ground station. From there, the data are flowing between the ground station and the mission control center, which happens usually over things like the Spacelink extension protocol, but also via just internet downloads of recorded telemetry files, for example. Then at the general control facility, you will also have things like a mission planning system and the flight dynamics system that will use the retrieved data to generate predictions and also to generate plans for the commands and the maneuvers to be executed on the spacecraft. And all of these systems will exchange information via some kinds of files and some file exchange systems. And finally, usually there will also be a data dissemination system attached to the mission control that will provide data to external parties. And now let's see what attackers could be doing in the system. So firstly, you can see if the attacker has an own rogue ground station, what they could try to do is to jam the reception of telecommands on board of the spacecraft, but they could also send their own rogue commands directly to the spacecraft and hope they would be executed. But they could also just eavesdrop on whatever is sent to the ground by the spacecraft. Now, if we go one step further, if we have an actual legitimate ground station that's being compromised by an adversary, what could be done? Well, the adversary could simply sit next to it and jam the reception of commands, telemetry that's coming down to Earth for this ground station. They could also just, again, be listening, but they could also even be spoofing and faking telemetry signals that are arriving there. And if they are now actually inside this ground station, they can also try to send their own commands to the satellite via this actual legitimate ground station for the mission. And finally, they could also just sabotage the ground station to make sure it cannot be used anymore. Now, on the way to the mission control system, we could just interrupt the connection to make sure that a denial of service happens. We could, again, be listening. We could be injecting commands in the forward direction or spoofing the received telemetry in the backward direction as well. Now, if we've compromised the mission control system, again, from there the commands are being sent, so an attacker could be sending commands. You could also manipulate the configuration to make sure it malfunctions, maybe sends different commands when an operator is trying to send something. They could also, again, spoof the data that's received by it and even sabotage the functionality to make sure that the mission, maybe in a critical time, cannot be commanded properly. Now, if we look behind the mission control system, basically in these flight dynamics and mission planning parts, what you could be doing is you could be injecting some malicious files as well and basically spoofing what's in there, manipulating them slightly. So if they would be used by the operators, the consequences could again be bad for the mission. And what can we do to detect these attacks? Then basically what we could try to do is collecting the recorded telemetry files at the ground station. We could also collect the telecommands that are sent by the mission control system. We could collect the telemetry that's actually received not at the ground station but at the mission control system. In general, from all the logs, the applications in the ground system, we should be collecting the logs to see if there's some suspicious activity. And also we should collect the information from the flight dynamics and the mission planning system to see what has been going on there. And yes, then there's also some additional data sources to consider that are not specifically part of this ground system. So this could be general weather data for the ground systems, weather data for the space itself, and also some general space surveillance information, and possibly even radio frequency monitoring information. And by correlating all of these information, and yeah, the correlation really is key here, we might not only be able to detect attacks that are not detectable by looking at a single data source, but also to distinguish some attacks from things that are just random faults. So for example, if there's a big solar storm, we might see that in the space weather information and might be able to distinguish that from a jamming attack by an adversary. Yes, and using all of this information, the way we are collecting data for the AI segment project is that we are using an actual ESA-operated space mission. And from this mission, we are collecting data from all of these data sources, or have collected it for one time frame from all of them, so they could be properly correlated. And the data volume there would be roughly 8 gigabytes per week, so this is really just a rough estimate. And yeah, for these collected data, the general nature is all of them are, of course, time series data. All of them are somehow generated at some time. And depending on the systems that you collect from, it's also possible that there are gaps in the data. And one thing that's also very common is that the data are quite periodic or sometimes repetitive because, well, the mission has, of course, repeating patterns. It goes around the Earth basically in a circle, and things might happen again and again and again. And the data types themselves, they're quite mixed, so it might be just binary data, some semi-structured data like XML or JSON, or just pure text data. And the formats themselves are often quite domain-specific. And from all of this collection, there are some challenges arising. These are mainly, firstly, there are no actual real-world examples of cyber attacks on the mission that we have as our sample mission. So all of the data that we are collecting are in general unlabeled. So this will, of course, restrict the amount of machine learning methods that you can use. And also, in general, the collection itself is already a challenge if you're collecting from such a large amount of data sources. And to do this, basically what you require is often domain-specific knowledge across all of these different areas of the ground system. And now using these collected data, we are implementing the system basically in the following way. So for the AI modeling techniques, we are basically only able to use algorithms that can work on unlabeled data, for example, in the sense of one-class classification. And the general technical source of algorithms that was chosen for the project was the PyOD library for different algorithms to be used. I'm actually not going to go in many more details, as this is not my main expertise area. And the whole detection system is being implemented on the platform called AI Enabler, which is also an ESA activity which has been done. And this platform provides you basically a framework for implementing AI applications following the MLOps principles. And it provides basically the possibility to implement machine learning pipelines based on the Kubeflow technique. And one special thing about AI Enabler is that it can already interface to various of the ESA mission data sources, which will allow, of course, also the AI segment system to retrieve data from them. And that's concerning both live data and also archived data from the past. So using this, we've crafted an architecture for the anomaly detection system, which is shown simplified here. So what you can see is the data is coming in from the various mission data systems. It's passed into the system via a request manager, basically, and we've partitioned it now into a development and a production component. And so we're in one component, we're training the models on these data, and when the model is finished, it's going into the production component, where the data are then passed into the live inferencing for the anomaly detection. And in here you can also see one more important feature, which is the external system shown up here. As basically the AI segment is able to forward information and alerts also to external systems, like the ESA CSOC systems that is being talked about every now and then here as well. And yes, now that we've talked about all this, one of the main challenges is still remaining, and that is how can we even validate this system? As I've said, all of the data are purely unlabeled, and now we might be able to train a machine learning system on it, but to evaluate it, we still need to know if its predictions are correct or not. So we need to have some ground truth of both data with attacks and without attacks, else we can only validate one side. And we want to be able to capture these attacks without them having previously taken place on the mission. So we decided to do this. Well, we will just run some attacks. However, as you might have thought, we are not running the attacks on the actual mission, as we do not have the cybercube yet. But what we've done is we are using the real mission data system applications, and we've created a data generation environment from them. So the real applications, this means we are using the operational simulator for the space mission. We are using the real deployment of the real mission control system, and we're using some other real applications like the file exchange system and also the data dissemination, together with the other applications which are mocked, so the mission planning and the file dynamics are not fully executed by us. And yeah, this is used to generate data also containing attacks, and I will quickly go over how this can be done. Basically, on the side of the control center, you can see well, the flight dynamics and mission planning files, we can just manipulate them by hand. They're basically text files. On the other hand, the mission control system and the connection to the ground station, this can be attacked using common penetration testing tools, sometimes with custom adaptations, so then they will become custom tools, of course, and also normal networking tools, and sometimes even manual intervention, for example, to send some malicious commands from the mission control system. On the other side, we now have the operational simulator, and basically some information for some of you who might not know what it is. It's normally being used to train the flight control team of the mission in order to prepare them for any things that might occur during the mission before they do it on the real satellite. And because of this, the operational simulator has many capabilities that allow you to mess with all kinds of things on the satellite itself, but also on every part that's being simulated. So the simulator contains not only the satellite, but also the ground stations, by the way. And yeah, so through these capabilities, we can repurpose them to mitigate, to make it look like attacks are taking place. For example, we can change the functions at the ground station to inject commands directly there. We can reduce the signal strength of the received telemetry until it's completely impossible to receive it. We can also just sabotage the components by making them fail. And yeah, on the spacecraft itself, we can again manipulate all of the functions and components on board of the spacecraft, and also even the orbit and the attitude in which the satellites are flying. And then also we can simulate row ground stations, basically by injecting commands that will be received by the spacecraft antennas directly without having been sent by the mission control system or the ground stations first. And this allows us to basically also prevent the reception of commands at the spacecraft and induce errors in them. And using all of this, we are able to now simulate the attacks on the satellite. We're doing this basically in a reproducible environment using an attack orchestrator. And all of this is being basically orchestrated by scripts across the various machines. And well, after running an attack, we are collecting the data from the environment. This could be just collection of files from the data dissemination or directly from databases. And we are labeling them then with the attacks that we've actually executed to be used in the AI system. And then we can ingest them into an AI enabler to be used by AISECMON. So all of this is currently in active development, and this would actually be the finish of our talk. And I would thank you for your attention and hope we have some interesting questions. In case we don't manage to address all of them, feel free to pass by at our booth and also to read the paper, especially about the first part of the presentation, which was published at the SpaceSec workshop. Thank you.
Thank you very much, Peter and Alexandra. So we actually have some questions. I will start with the audience here. Okay. So then I guess I will move to the questions Oh, sorry, not this one. Okay, so. Okay. So we have a question from Kimberly King. So I will be reading the question. It would be, have you considered how the threat landscape changes with meshed satellite via ISLs versus an individual satellite?
So at the moment, in this stage of the study, we have not considered constellations that are also having inter-satellite links. So at the moment, basically, the missions we've been considering might be constellations, but not with links between the satellites. But this might, of course, be, for example, changed in further iterations of the studies or extensions of the project.
Okay. And I have another question from Paul Svan Clark. He says, is there a plan for ESA to update the risk assessment tools to include the AI threats you identify are lacking? I mean, if you have the information.
So as I mentioned, our goal was to have like the basis to start the discussion, and now, of course, it makes sense to start actually discussing and updating accordingly our risk analysis and maybe also the existing knowledge bases. But we are just very much at the start. So,
Okay.
Yes.
Yeah, thank you. Yes.
Hi, Wouterloo from the NLR. Thank you for your presentation. It was really interesting. I was wondering for the simulations, is that purely for the mission? Is that shareable in any kind of way? And same question about the data.
Well, so at the moment, as all of this is being conducted as an ESA activity, at the moment we are not able to share any of these artifacts, I would say.
Mm-hmm.
After the project has been finished, in the end the decision would be up to ESA if all of or any of these things are to be published or not. So in general, for example, the simulator itself is already belonging to ESA. It's basically made for the mission, not for us. And so in the end, we personally cannot publish the simulator, so there it would be up to ESA. And I'm not sure if it's realistic that it will be published, but yeah, that's what we will be able to see at the finish of the project.
So it's not based on the NanoSat MO framework then?
Sorry, could you repeat?
Is that based on the NanoSat MO framework, the mission operation framework?
No,
or something else?
No, the operational simulator for the ESA missions is usually based on other frameworks, I believe.
Thank you.
Okay. We have a last question.
Hello, Satya from the Cyber Agentur. I have two questions, really. One is related to what was just asked. Is it possible to, is it thought of at least as the architecture to have it as a software and hardware independent? That way other softwares and other hardwares can be tested? That is the first question. And the second question is a more generic question. I think you're trying to do that, but generally with AI, you need to have multiple training data, and it's often, I mean, attacks are fortunately, generally, but unfortunately for you, very low in number. So how do you try to make that work?
Yes, so for the first part of the question, at the moment, what we've been doing in this test environment and for the simulations is, I would say, purely tailored to this specific mission that we're working with. But in the end, through the expertise we've gained, it would be, and also through the initial analysis that we've done, it would be much quicker to set this up for a different mission than before, I would say. And for the second part, as I've said in the presentation, all the data we have are purely unlabeled, and we have to make the assumption that they are just consisting to the one class that does not have attacks in it. So we have basically no indications of any previous attacks on the mission, and we cannot train using them. So we purely train using data without attacks, trying to recognize the normal state of the mission, and will then detect anomalies that deviate from it. And to validate, we are able to use the data we've generated in this validation environment, which we cannot recommend directly for training, as the amount of data that had to be generated and the variety that has to be generated for training would be much higher to avoid things like overfitting the models.